Hello, good morning. I'm Shannon Colbert.
I'm Kathleen Luo.
I'm Allison Park,
And I'm Brandon Spitzer.
and we research the development and characterization of plastic composites. So what is material science? It's a field that encompasses physics, engineering, and chemistry to find the effective applications of materials. For our research purposes, we'll be focusing on plastic polymer composites and how we can look into certain immiscible polymer blends to find the best beneficial and respective properties of each blend. The graphic is just a visual representation of how MatSci encompasses the characterization, processing, and simulation of different materials. So the two plastic polymers that we will be using were polystyrene and high-density polyethylene. Polystyrene is a thermoplastic with an amorphous structure, and despite this amorphousness, it's still relatively very stiff. The other material that we used was high-density polyethylene, which is also thermoplastic, but instead it's semi-crystalline and it has a tough structure. The abbreviation we'll be referring to for polystyrene is PS, and the abbreviation for high-density polyethylene is HDPE. It's important to note that polystyrene is most famously used in styrofoam, as held by Brandon's, and HDPE is most famously used in plastic bottles.
As Ali mentioned, the two composites we'll be making are combining polystyrene and high-density polyethylene. These plastics are being used because they're very cheap, they're versatile and commonly used. We will be increasing the weight percentage of polystyrene, increasing from 0% to 20%, 35, 50, 65, 80 to 100% polystyrene. And we hope to increase the stiffness of polystyrene and maximize on the toughness of high-density polyethylene. Our main goal is to characterize polystyrene and high-density polyethylene composites that were prepared using a unique single-screw extrusion melting process method. We will be characterizing them for their mechanical, thermal, and structural properties through flexural and impact testing, differential skin calorimetry, and infrared spectroscopy. Our goal is to find the ideal percentage for the composite, and this will show the most beneficial characteristics.
So the different compositions, the 7 different ones that we used, were made by the Randcastle company, and they use a single screw extrusion method. And so how this works is they put the raw forms of polystyrene and HDPE into the funnel of the extruder, and then the plastics move in and they're combined. And as they move along, there's heaters that raise the plastic mix to a certain temperature. And as they move through this screw as well, there's a high shearing process that occurs. And shearing is where the forces are applied tangential to the surface. So if you had a square of plastic here, the forces would be applied like this, and all of the molecules would move together in that way. And they found that that is the most effective way to combine them to produce the immiscible polymer blends. So once they move out the end of the screw, they're extruded and they are put into a pelletized forms and cooled down. And these pellets are what we use to mold and characterize.
So once we have these pellets, in order to make the bars that we'll be testing, we use an injection molder. So we put the pellets into the funnel and waited for it to melt into the mold, which is held there by a vise. And so here are 2 examples of successful bars that we made. You can tell that they're successful because the plastic reached the bottom of the molds, creating perfectly clean-cut corners. In order to create the bars for the different composites, we had to use different temperatures and pressures to process them. And as you can see, the higher the percentage of polystyrene we use, the higher the temperature and pressure.
So one of the first tests that we completed upon our specimens was impact testing. Impact testing is a destructive mechanical test that's meant to measure how much energy is absorbed once this test specimen is impacted by a swinging pendulum, as seen in the diagram. We used a machine that's called the Instron Dynatop POE 2000, and we followed the American Standardized Test Method of D6256, and we tested 5 samples. And it's important to note that this was a standard machine, so each time we had the impact, the pendulum energy had a value of 21.7 joules, and the velocity was 3.46 meters per second. So in our results, we noticed that all the specimens underwent a hinge fracture type. This is important because that just means that the piece itself didn't have a complete fracture. It still retained like attachment. And as you see in our graph, we had two like big outliers that didn't follow like a downward trend, and further research needs to be done to really evaluate why this occurred, because it's known from prior research that the greater the polystyrene percentage and HDPE, the like consistent lower trend there should be for the impact strength.
So the second test we conducted on our specimens was flexural testing, which tests for stiffness of a material. So we used a 3-point loading system, and so the bar is placed across two supports, and a load cell is brought down on it, and so the force is placed on it, and we graph it as a function of displacement. We collected stress-strain curves as our data, and we followed the ASTM D790, and 5 samples were tested for composition. In our results, we concluded that the higher the percentage of polystyrene, the stiffer it is, which is shown by the modulus, which is a slope from the first graph, and is a consistent increase.
The next test we did was a thermal property test, and we used the Q1000 differential scanning calorimeter, or DSC. It was a thermal analysis that measured for temperature and heat flow, and the method we used was the heat-cool-heat method, which means that the sample started at 0 degrees Celsius and was heated up to 200 degrees Celsius, then back to 0, and then again for reheating back to 200 degrees Celsius. And this was run at a rate of 10 degrees Celsius per minute, and we tested 2 samples per composite. Here are some images of the materials we used to prepare for the DSC analysis. First, we cut a tensile bar. We made tiny little squares about 3.5 millimeters by 1 millimeter thick, and placed them into small aluminum pans that were measured using a high precision scale, and those measured out to about 8 milligrams. They were then later encapsulated using a T0 press and transferred into the DSC autosampler. After the scan was run, the first graph that was produced was the first heating curve, and this shows the melting temperature of the composites, and throughout all the composites, the temperature remained consistent even with increasing polystyrene concentration. And the next graph that was produced was the cooling section, and then this just shows that the crystallization temperature also remained constant with increasing polystyrene content, and the glass transition also remained fairly constant, slightly decreasing, and a major gap or a significant gap between the 35% and 50% polystyrene. The last graph that was produced was the reheating curve, and this also just shows the melting temperature, which also remained constant at around 130 degrees Celsius.
Sorry.
Now, this is useful for knowing that even as the polystyrene content increased, that the melting temperature remained consistent throughout, showing that the mechanical properties were not compromised even with increasing temperature. By taking the area under each curve, we were able to get the melting heat of fusion and heat of crystallization, which showed a steady decrease as polystyrene content increased.
The fourth test we used to characterize the composites that we tested was Fourier transform infrared spectroscopy, which is more easily known as FTIR. And this is a very precise machine. So before testing, we would clean the crystal that's actually in the machine, and each sample we would wipe it down with ethanol to remove any residual oils from handling or any materials or dust that could be on the surface that would skew our results. Next, we clamp the sample into the FTIR, and this ensures that the sample is held directly on the crystal for analysis. And then we execute the test, which consists of the FTIR shooting various wavelengths of light through the sample, and what it returns is a graph of the absorbance at various wave numbers. And so here are our results from each of the composites that we tested. We overlaid them, so this is all of our data from the FTIR. And here we have zoomed in pictures. from the previous graph that I showed. And so the first one is from wave number 3000 to 2800. And the two peaks that you mainly see here show characteristics of HDPE. And so you can see the trend in the data that as the HDPE percentage in the composites decreases, the absorbance at each level also decreases. And then if you look to the right, it's from wave number 1350 to 950, and these show the peaks that are associated with characteristics of PS. And so here you see the opposite trend occurring, whereas the polystyrene percentage increases, the absorbance also increases. And so the FTIR tests confirm that what we think is in the compositions, the various percentages, really are, as you see, the trends are continual across our samples. And also, the FTIR also shows that there really is just polystyrene and HDPE in our samples because there is no presence of peaks occurring at any other areas. And every sample showed a peak in absorbance at the same point, so there was no outlying data that would have shown the presence of contaminants.
So to conclude our research, we were able to hit upon the flexural impact, structural, and thermal properties of our immiscible polymer blends by our 4 different tests. It's important to note that we want to do further evaluation of our impact tests to see why we had the 2 outliers. We also noticed that the thermal melting point and crystallization temperatures were consistent with our increasing polystyrene, and we also noticed that the blend of the 80 polystyrene HDPE had the greatest toughness, and our FTIR results just gave us the accuracy we needed of confirming what our blends were composed of.
As for our applications, our PS and HDPE composites are already used, and they're usually used in barrel ties, pilings, I-beams, high-load and high-load capacity bridges, and in the future we hope to find a better processing method to produce product variability.
If we had further time to conduct additional research with these composites, as Ali mentioned, we would like to do further impact testing and see why our results had numbers that didn't follow trends from previous research. And in addition, we'd like to do a morphology analysis. And this is done with a scanning electron microscope. And so we'd like to look at our samples at a molecular level. And this can tell us more details about the how the polystyrene and HDPE are actually interacting with each other and how they're blended in the samples. And we'd like to compare our analysis against the analysis that was done for how Randcastle previously made these composites, and that would show us if their industrial processing methods resulted in any difference in their final product.
This research would not have been possible without the help of our mentors Dr. Lynch and her grad assistant Elizabeth Chang, our RTA liaison Apurva Agarwal, our RTAs Brian Lai and Nicholas Ferrer for their help in writing our papers, Dean Rosen and Dean Antoine for creating this GSET program for us, the Rutgers University and State of New Jersey, our corporate sponsors Lockheed Martin, Silverline, and Rubix, and other GSET alumni and sponsors.
Thank you. Are there any questions?
Feel free.
Know everything.
Yes?
I found it interesting that you used a lot of equipment for various tests. Was that something you had used before, or what was that experience like for you?
So we spent a lot of time learning how to use these different machines, and that was a really great experience.
Mm-hmm. So no, we haven't touched them before, so it's really
It
good.
was a new experience for all of us.
Unless I misunderstood, first of all, very well done for the nuclear topic, I'm sure.
Thank you.
Experiments. Some of the graphs, it looked like the sample size was a bit short. It appeared to me, maybe I must misinterpreted it. Did that, were you concerned that that would be affecting your statistical analysis interpretation of the results?
So we had to personally make all of our bars that we used to test, and originally we had made a lot of tensile bars because we just had the expectation that the Rutgers machinery would be able to be like used then, but it ended up not working out, which is fine. But so yeah, we were a little concerned, and that's why some of our data is like not as consistent, but it's okay.
And also, in addition to that, as we molded the higher percentages of polystyrene, we found it became more difficult, and we had the chart showing the temperature and pressure. But the molding process is like very finicky because we were doing it manually, so that's also the reason that we couldn't get good molds of all of the samples.
Back.
Quick question, is PS and HDPE, right?
Yeah.
HDPE, when they blend together under high temperature of gas, right? Do they form a chemical bond between them?
No, it's only a physical bond because the two plastics are immiscible, and so the only way we would mix them is still like a heterogeneous mixture. They're just like, the molecules are really close together, so it seems like it's one composite.
So it's just physical blend.
Yes.
That's why analyzing like the processes is so important because it is very difficult to mix them, and so there's like a constant optimization of the process, and that's why we actually perform this analysis to see how well they really are mixed and what kind of properties they show us.
Thank you.
And the front.
Have any of you ever had exposure to material science before, and did this project maybe inspire you to pursue this further when you entered college?
I didn't have any experience, but it definitely piqued my interest. And during my time at GSET, I also was able to take a material science course, and that was definitely my favorite class here. So
the extrusion temperature and the injection molding temperature, how you guys control and how you define the temperature to use?
So the machine.
Oh, a lot of it is just like trial and error. It's like if it didn't melt fast enough, if you had the like temperature, the pressure was too low, it wouldn't flow all the way through. So a lot of it was just like trial and error. We made like a tons of bars to figure out what the best temperature and pressure was for each one of the composites.
But actually, DSC tell you the melting temperature, right? So can you maybe use that temperature so add another tank to DC or something like that?
I'm sorry, I couldn't hear.
The DSC tell you the melting temperature, right?
Of yeah.
Oh,
of
that's
the acid.
afterwards. Okay.
Yeah.
Yeah.
That was a.
We cut them from the tensile bars that we made.